Hello, my name is Rob Reynolds. Welcome to Calculus section 5.5. We're going to learn the substitution rule today, and I think I've already kind of taught the substitution rule. At least I've been talking about a U-sub when I did the chain rule for derivatives, and now we're going to kind of undo derivatives and look at how we can use U-subs for integration. 90% of the time, we're going to let u be the inside function. So if I have f at g at x, a composite function or a function within a function, I'm usually going to let u equal that inside function. Again, doesn't always work, but that's the first thing I would try at least. So the first example, you can see the inside function. You could spend time multiplying this all out and integrating each little sum. But it might be faster to do a u-sub. So if we let u be 2x plus 1, then du is 2dx because I'm taking the derivative with respect to x. Well, actually, maybe it'd make more sense because you did implicit differentiation. So if this is u, this is really du dx. I took the derivative of u with respect to x. But we just throw this dx over on this side because I have a 2 and a dx here. So that 2dx gets replaced with du. So all of this in yellow goes to du. Everything in here goes to u, and I still have it being cubed. And now all I have to do is integrate u cubed. So u cubed, again, you increase the exponent and then divide by it, and I'll say plus c. The last step might be just to go back and throw your u-sub back in there. How about 2x plus 1 to the 4th power divided by 4 plus c. Let's try it again. The inside function for this next problem is probably 10x. So we could let u equal 10x, then du would equal 10 dx. And the 10 and the dx conveniently all goes to my du. I can see I'm going to integrate e to the u because there's my u-sub, so e to the u, and I have that du, which is represented as a 10 dx. So again, when you do a u-sub, you're replacing all of your x's for u's, and then, of course, the integral of e to the u is just e to the u, and then plus c, and then you'd replace the u with whatever it says to go back to in terms of x. So there's part A. There's part B, and let's try again. Inside function, let u, by the way, you cannot multiply this. No, because you've got to take care of your exponents first. So this would be a nightmare to try to multiply. Oh, and you can't do, please stop. You can't do that either. So you can't multiply by x to the 4th. You can't distribute the 9. This would just be horrible if you didn't have u-subs. So with u-sub, though, it's not so bad, and especially since they gave me a 5x to the 4th, of course, plus 0. And so you don't have a 5, but I do have an x to the 4th, and I do have a dx. So I'm going to divide both sides by 5. So I get 1/5 du is going to replace all of this in my x's. So this and this gets replaced with 1/5 du. I'm going to pop out the 1/5, keep the integral of, now remember, this is my u, so all of that in yellow goes to u to the 9th, and then I have du represented by that x to the 4th dx. You can always pop out a constant, you just can't pop out variables like an x or a u. But the 1/5, yep, sure enough, comes popped out. So now I'm going to integrate this. The 1/5 is just a constant, it stays there. Increase the exponent, because that's what integration does. Divide by the exponent. And I've got a 1/50th x to the 5th plus 6 raised to the 10th plus c. My dog is thirsty. I don't know if you can hear him lapping up water in the background, but he is. The inside function, it looks like if you were to say cosine x cubed, it looks like the inside function is cosine x. So I'm going to let u equal cosine x, and du would be negative sine x dx, and then probably divide through by -1. So I'm going to pop out a -1. do my u sub, so this gets replaced with u cubed, and conveniently enough, all of this goes to du, and so I'll replace all of this with du, because that's what it's, and of course I popped out the negative already. The integral of u cubed is negative cosine the fourth divided by 4 of x. You could have gone through u, but I just kind of skipped that step. So again, here's the author's explanation for A. Here's the step I skipped for the author explanation for B. And of course, all of these solutions are posted on Blackboard, and I hope you have printed off this problem on a PDF file, and you can try it. You just pause the video and see if you can figure out what to let u be. I would personally let u equal x plus 1. And so then du would equal, this is a trick. You haven't seen this yet before. So du is simply dx. Now, remember, you cannot, don't write this, you can't have x over the square root of u. You can't, and then this is du. You can't have an x and a u in the problem, but there's a little trick here. You can solve for x, because x is really u minus 1. So let's replace this up here with that u minus 1. And then we can use some integration techniques by rewriting this as u to the 1/2, because the square root radical is raised to the 1/2. And then I'm going to say u over the 1/2. It's rare that it's called decomposing the fraction. So I'm going to decompose that. I normally start at A, where I have a common denominator, and I subtract and combine it to B. But in calculus, oftentimes we start with one fraction and we want to break it up, because once you have part A, then you can go to part C and rewrite this thing as u to the 1/2 minus u to the negative 1/2. Then, of course, integration means increase it by 1. So 1/2 plus 2/2 is 3/2. Divide by 3/2, which is 2/3, minus 2u to the 1/2. And then, of course, you have a plus c, and then you go back and replace u, because u was the x plus 1, and then you'll have the author's answer here, plus c. Remember that plus constant. So what's the substitution to? An alternate way to work this problem. Looks like they work the problem out a little bit differently. It's clever, nice. So, but same answer. So substitution rule for definite integrals, you do the exact same thing, but then when all is said and done, you evaluate it from A to B. But remember, this A and B are going to change if you do a u sub. The parameters might change. So that 0 and 2 is only good for x values. If you do a let u is equal to x plus 3 u sub, then that 0, 2 is going to be renamed, because you're going to plug the 0 in there and the 2 in there, and you'll have new parameters. Let me show you what I mean. So if u is the inside function x plus 3, du is just dx. So I've got the integral of 1 over u cubed du, but it's no longer 0 because it's in terms of u now. So 0 plus 3 is 3, and then this 2 up here, I tried to get it up green. This 2 gets plugged in there and turns into a 5, and so the 0, 2 goes to a 3 and a 5 in terms of u. So I would encourage you to do that. You could always go back to x's and throw in the 0 and the 2 for your fundamental theorem of calculus, but this is a nice principle, especially when you hit Calc 2. Practice changing your 0, 2 to 3 and 5 in terms of u. You'll be better off. So I'm going to integrate from 3 to 5. I'll just set it up so you can integrate nicely here. So what is this? Negative 1/2 u to the negative second, because you're going to increase negative 3 to a negative 2, and then evaluate it from negative 3 to 5. Now, again, if you wanted to, you could. I wouldn't recommend it, but you could do negative u divided by 2, and then still replace that u with that u sub, which was that x plus 3, right? And then, well, and the negative exponent throws it back in the denominator. So instead of going from 3 to 5, you could, I don't even want to show it to you because I don't want you to do this, but you could throw the u back in there with a negative exponent. It's going to make that thing a positive 2, and then go back to 0 and 2. And then from here, you could do the f of 2 minus the f of 0, the fundamental theorem of calculus. I really don't, this will work. I would not take off. I'll give you 100% credit for the black, but I'm telling you the green is easier. It's going to service you well, especially moving forward when we get into more difficult problems. It's just easier to evaluate the green. I don't know if I can convince you with this problem or not. Let's see, I'll just keep that negative 1/2 out there and then try the f of 5 minus f of 3, and then I'll pray to the good Lord that I get the same answer. Just to show you that 90% of the time this is going to be a little bit easier. So this is 5 to the negative second, which is 1/25, minus 3 to the negative second. Well, 3 to the negative second is 1 over 3 squared, or 1/9. I went to my calculator and I punched it in because I've shown the fundamental theorem of calculus. There's my f of b minus f of a, and I don't care about the number crunch, but you can see it turns out to be the exact same answer. So if you went from step A, this guy, to step B, the answer, that's fine. You've shown me the calculus, you've demonstrated your content knowledge. I don't need to see the number crunching of finding common denominators and adding fractions. That's not what I'm testing over. But I do like for you to show me the f of b minus the f of a. Don't skip that step because, well, honestly, if you don't know how, I could show you, but you could just type this into the calculator. Math 9, math 9 brings up, I'll show you, and then just hitting math, enter, enter. So, to show me that you're not cheating, then yes, I can. So, but again, math 9, if you have a TI-84, we'll just set this integral up, and then you could work the problem very quickly. But I'm interested in you convincing me that you're not using your calculator through that process. This one, I think you have to do another u sub. So if you let u equal x squared plus 1, du is 2x dx. I love the x dx because I see an x dx here. I just got to get rid of the 2, and I could do that by dividing through by 2 and pop out a 1/2. It shouldn't write in red because you're going to get that problem mixed up with the other problem. So let's stay in blue. So 1/2 the integral, and then see this x, I got to get rid of it. Ooh. Oh, no, I already did get rid of that x. That x goes with this. So I don't have to do it. I was thinking I needed to solve for this x here in terms of u, but I think all of this is gone. It gets replaced with 1/2 du. I pop out the 1/2. There's my du. And then I just have 1 over, oh, great. All of this is my u, and so just 1 over u. And if you remember, the integral of 1 over u is my natural log of u, which, again, I'll show it to you, but I really don't want you to go from 0 to 4. I think it would be nicer. You could do step D, but I would prefer step E, only because I know where you're going to in Calc 2, and step E will help you more when you get to Calc 2, which means instead of between 0 and 4 in terms of x, all you'd have to do is throw the 0 right in here, 0 squared plus 1, and make it a 1, and throw the 4 in here, 4, 16, 17, and then evaluate this. I really think that's going to be a little bit nicer. So the 1/2 stays out there, and it's the ln of 17 minus the ln of 1. And if you remember, the ln of 1 is 0, and so the final answer is 1/2 the ln of 17. Of course, you could go decimal, but I'm not interested in you, well, unless my math lab says round to the nearest decimal, but I would much prefer the exact answer, 1/2 ln 17. So it looks like the inside function here is sine x is inside this raised to the 4th power, so I'd probably let the inside function, which has worked 100% of the time, but it doesn't always. I should show you an example where it doesn't work. Du is the cosine x, how convenient, dx, all of this. So all of this goes to du, and I have the integral of u to the 4th du, and I would change my 0. Oh, I got to do a little bit of trig here. So if I throw a 0 in right here, the sign of 0 is what? There's 1, 0, there's the cosine, there's the sine, and it's still 0. And then if I throw a pi over 2, the sign of pi over 2 is over here, so 0, 1, and I think it's a 1. Oh my gosh, this is much easier. I don't know if it's much easier, but think about doing this. So this is going to be 1/5 u to the 5th from 0 to 1, and then when I do my fundamental theorem of calculus, I just get 1 minus 0, 1/5 times 1 minus 0, which is just 1/5. One last thing before I end the video. Oh, by the way, here I worked out solutions from the author, which of course are posted on Blackboard. So go look at these. And how, oh, I love that the author did this in terms of u and changed this 0 to a 0. Well, actually didn't change, but he did do this. He's showing you how to change those parameters. Excellent. I like the author. This last one, you needed to use some trig identities. These are your half angle identities. Perhaps you've seen them like with the square root, just the sine x. But we're going to find out that it's kind of helpful to keep it in terms of sine squared and cosine squared. So I'll have to give you these identities. I don't expect you to memorize them, but I don't even know if there's anything off of the test, but I know the homework has some of this stuff. So let me show you. This cosine squared, we can rewrite this thing as, because I mean, you could try a u sub. You could say, oh, here's where your u sub doesn't work. So if you let cosine be my u, then my du is negative sine, and we just don't have a negative sign. I can't do anything. So that just didn't work. So we have to use a trig identity and replace all of this with the integral of 1 plus cosine 2x over 2, which is really that 1/2 the cosine of 2x divided by 2. And then I integrate the 1/2 plus the integral. I can pop out a 1/2 the cosine of 2x. And then that makes the problem a lot easier because the integral of 1/2, remember, you're in terms of d theta this time instead of dx. So when I integrate this, this becomes 1/2 theta instead of 1/2 x. 1/2 stays out here. Now this is tricky. Here you could do a u sub. You could let u equal 2x, du is 2dx, and then you have to divide by another 2 and pop that out. So another 1/2 pops out. That's from this red. So this 1/2 is this 1/2. And then you've got the integral of just cosine u, and of course that's excuse me, I had to think about whether it's positive or negative. But I think it's positive because the derivative of sine is cosine. So positive sine, then the u, I'll replace the u back with my 2 theta. Well, I went theta this time. I told you not to do that, but if you wanted to, we could put everything in terms of u, but I didn't in this case because this already has a theta in it, and I didn't do a u sub there. And I did do a u sub over here, so I don't want half of the problem in theta and half the problem in u, so I'll go back to theta, and then I'm going to do the fundamental theorem of calculus in here, and well, I could pop out a 1. So the 1/2, I could do theta plus 1/2 sine. That'll clean it up just a little, not much, between 0 and pi over 2. So that 1/2, at least I don't have to worry about that. Let's see, let's do the fundamental theorem of calculus. So plug in pi over 2. Let's see, 1/2. This is the sine of pi, and the sine of pi is 0, and so that wipes this out. Minus, so this is your f of b minus f of a, which would be 0 plus 1/2, and then what's the sine of 0? Well, that's also 0. Kind of something like that. So there's my f of b, there's my f of a. Looks like I have a bunch of zeros in here, and the only thing left is this 1/2 times pi over 2, which is pi over 4. Good. And let's see if I think good. Yay, the author has the same thing. They did something a little bit. Oh, they didn't factor out that 1/2 like I did, so they had a pi over 4 from the get-go, but they had a bunch of zeros as well. So I'm going to end the video here, even though there's a little bit more practice. So number 19, again, worked out solutions. I would definitely try these. These are some good problems right out of the book is where I'm pulling these from. But you should definitely be work. Oh, this one's really good because you have to integrate and use a trig formula, which is really rough because this guy is, ooh, good luck. Because remember that cosine squared is 1 plus cosine of 2 theta, and this theta happens. Oh, that's a rough problem. But fortunately for you, it's worked out here. So give it a shot. See if you can work that out. If you have questions, shoot me an email, and I'll try to help you. Good luck.